All right. Yesterday, we talked about geometric sequences. We verified if something was a geometric sequence. We found the formula, or we looked at the formula for finding the rule if you're given the sequence. We graphed, and we found the sequence given a single term and our common ratio. And then we found the formula for the sequence where you're given two random terms. And I was super nice to you on the homework, and I think I gave you 3 of them where one of the random terms was your first term. So it was fun to see people who didn't notice that, and they plugged in to solve for A1, and then they got a 0 exponent, and it was your A1. So that was fun. So today we're going to talk about geometric series. Geometric series. So a definition to start. The expression formed by adding the terms of a geometric sequence is called a geometric series. Geometric series. So the sum of the first n terms of a geometric series is denoted by the s sub n. So that's what we saw with the arithmetic series as well. There is no differentiation between the two series in terms of this notation. So just remember, s sub n is a series, a sub n is a sequence. All right, now here's my first big mistake. I pulled this from your text. Well, this is a picture in your textbook, and I Googled it online, and I put it in the notes without realizing that this is the sum of an infinite geometric series, which is great, but we need to look at the sum of a finite geometric series. So cross this off. It's a perfectly good formula, but it's not what we're using today. You'll see it in the next notes. We want the sum of a finite geometric series. Because an infinite is not as helpful to us. So the sum of a finite geometric series is given to us by s sub n equal to a1, our first term, times 1 minus r to the n over 1 minus r. That is the formula we want to use. We are going to see very large numbers today. So if you think about, we noticed that arithmetic series were really like, or sequences were a linear line, right? And if these look like an exponential, the geometric sequences look like an exponential. If you add together exponential terms, obviously you're going to get really big numbers. So our first example, we want to find the sum of a geometric series. So we're given this series here. And I'll write down the general rule again. So we want our s sub n of our first term times 1 minus r to the n over 1 minus r. So some things that we need. The first thing we need our first term, and we need our r. Now, fortunately, our r is in this general rule, but we do need to solve for our first term. So to do that, we're just going to plug in a1 equals 4 times 3 to the 1 minus 1. And you're going to see this happens every time. This is a little silly. This would be 4 times 3 to the 0. Well, 3 to the 0 is just 1. So what's going to happen is it ends up being this first number. As long as it's I minus 1 here, it'll end up being 4. So my a sub 1 is just 4. And then I'll just rewrite my r again, but hopefully you can all see my r is just 3 because it's the base that's holding up this power. So then my formula for this series is going to be s, and now what is my maximum term here? 16. We're pulling it from this part up here. Equal to my first term, which we said was 4, times 1 minus r to the 6, not r, sorry, 1 minus 3 to the 16 over 1 minus 3. Okay, since these are such big numbers, just put it in your calculator. We'll have to be careful with our parentheses here. So what you would want to type is you do 4, and then you do double parenthesis, because we need a separate parenthesis for our numerator and a separate one for our denominator. So 4 times double parenthesis 1 minus 3 to the 16, close your first parenthesis, divided by another parenthesis 1 minus 3, and then close your double parenthesis. And as expected, this gives us a huge number. It gives us 86,093,440. So the first 16 terms in this sequence added together gives us 86,093,440. Questions about this formula? I think it's as straightforward as the other one, but you're going to see bigger numbers because of the fact that this is really an exponential. Okay, mistake number 2. I told you the other day that we really have to work with I equal to 1, right? And then your book, in its brilliance, has, in the practice questions, it has 2 that are I equals 0, and it just assumes that you know what to do. And I don't know why it does that. So flip your page over to the blank one. We're going to add an example here. We'll come back to that story problem. So we're adding an example. And we want to look at the sum from I equals 0 to 7 of 12 times negative 1/2 to the I. All right, so if you remember a couple homeworks ago when we were talking about rules, and I had mentioned if you start at I equals 0 or n equals 0, whatever we were looking at, that it made the rule easier and that there was a way to shift. There is a way to shift. So we can't put this through that geometric series formula right now because our n is not correct. We don't have a first, I mean, we do have a first term, but this is talking about the 0th term, and we want the A1 term, but that needs to be the first term. So there's a couple issues here. So we can change this. We can make this be equal to the sum of I equals 1. And now let's think about how many terms were in this original sequence. Not quite. 8 terms. Yeah, because you count 0. So I still want 8 terms. So I need to make this go up to 8. Then I'm still going to take the rule, again with one minor change. Yeah, I minus 1. I need to shift this back. So if you think about making that 0 again, just make it I minus 1. If we wanted to make this I equals negative 1, which I don't know why we'd ever do that, you'd make this I plus 1. Okay, you're kind of fixing this so it's back to the 0. Now this is what we can put through that kind of formula. So my general form again, I'm going to put that to the side, is S sub n equals our A1 times 1 minus r to the n over 1 minus r. I need my first term, so now I'm going to find my first term from this. So it would be 12 times negative 1/2 to the 1 minus 1. And remember, I said what would happen. That's always going to go away. And our first term will be 12. Notice if we had tried to find the first term here, it would not have been 12, right? Because this would have been negative 1 over 2 to the negative 1, and that wouldn't have gone away. My r here is negative 1/2. So when I put this through the formula, it will be, so S of 8, that'll be 12 times 1. Now, here's a little thing, just because we're going to type this into our calculator. If it's negative 1/2 raised to the 8th, what should we put into our calculators? Think about our signs. What's our calculator going to do? It's going to make it negative. And it should be, so if I was, and you don't have to write this, but if I was writing this correctly, it'd be negative 1/2 like this to the, not to the second, sorry, to the 8th. And if we don't put the parentheses in our calculator, it's going to tell us a negative number, and then it's going to do a negative, and it's going to make the top plus. And I don't want that to happen. So what you can do in your calculator, and we're going to just play this fast and loose, you could, if you're not going to put the parentheses, just forget the fact that it's negative in the first place and put positive 0.5. On the bottom, on the other hand, what's 1 minus negative 1/2? 1 plus 1/2. So you're going to make this a plus. And I put a double plus just to show you that conversion. So in your calculator, it's easier to type a decimal than a fraction, but if you need to type a fraction, then you have even more parentheses, but that's fine. So I'm going to type 12 times double parenthesis, and then it'll be 1 minus 0.5 to the 8th divided by 1 plus 0.5, close my double parentheses. Okay, I get a decimal. I want this as a fraction for your homework. So remember what you hit is then once you have a decimal, you hit math, enter, enter. So you should get 255 over 32. Now some issues that we ran into second hour. For whatever reason, a couple people's calculators, it'll turn most of the decimals into a fraction, but there's one that was like deemed too big or something and it didn't turn it into a fraction. So they had to look off of a friend's. That's not an issue for a test or quiz. For Go Formative, I tend to be a little stricter with formatting just because I like us to get into the habit of using it. But I understand that on a test or quiz, I'm more interested in you knowing the concepts. So if your calculator happens to be one of those unfortunate calculators doing that, just look off a friend, make sure your decimals were the same, and then put in the correct fraction. Test or quiz, it doesn't matter. Questions about that one? So you have one series on your homework that's going to start at 0, and you'll have to shift it before you find the series. The last problem I want to do with you is that story problem, because I think it's a really nice way to round out this section. So flip back to example 6. So this is asking us to use a geometric sequence and series in real life. And I'm curious if you'll recognize a function that pops out of here. So this is about movie revenue. So in 1990, the total box office revenue at US movie theaters was about $5.02 billion. From 1990 through 2003, the total box office revenue increased by about 5.9% per year. So part A wants us to write a rule for the total box office revenue A sub n in billions of dollars in terms of the year. We're going to let n equals 1 represent 1990. So remember our general formula here is A sub n equals our A1 times R to the n minus 1. That was the formula we saw yesterday. So I need my A1 and I need my R. Does anyone know what is my first term in this sequence? Yeah, it's that 5.02 billion technically, but we're just going to do 5.02. Because that's my initial profit or initial revenue, rather, that I made in that first year. How about my rate or my R? I'm calling it a rate, which it is. But what is my R here? Yeah, and close. So what do I need to, if I do 0.059, won't that just give me 5.9% of the revenue?
So you need to
Close. I need to add it to 1. Yeah, so you do 1 plus 0.059. Yeah, this is going to be our growth formula. Do you guys recognize that when you did, I think it was in chapter 4 or 3, I don't remember, where you did like the compound interest rate and the appreciates and depreciates. You had an A equals P times 1 plus R to the T, kind of. This is what this is. So any sequence term would be that initial amount times 1.059 raised to the n minus 1. So any n that I plug in there will give me how much money the theaters made in that year. So if I plug in 2, it would give me how much the theaters made in 1991. If I plugged in 5, it would give me how much money they made in 1996. So part B says, what was the total box office revenue at US movie theaters for the entire period 1990 to 2003? So first of all, how much time has passed? Basically 14 years. So if it's 14 years, do I just plug in 14 for my n here?
No, you have to because you have to add.
Yeah, so if I plug in 14 here, it's going to give me how much money they made in 2003, but I want the total. So this is the difference between a sequence to a series. So really what I'm looking for, I'm not looking for A14, I'm looking for S14. So now I'm going to apply that formula that we saw today. So my S14 is going to be equal to A1 times 1 minus R to the 14 over 1 minus R. And we already have our A1 and we actually have our R as well. So this really will be 5.02 times 1 minus 1.059 raised to the 14 over 1 minus 1.059, which I won't make you type into your calculator, but you should get that it's approximately $105 billion that they made over this 14-year period. That kind of makes sense? I think it's a cool connection. We see a formula that we've seen chapters ago. We get an application for a sequence 2 series and see the difference there. So you have one homework problem that looks similar to this. It's not about revenue, it's about skydivers, but it's the same idea where you're looking at a sequence versus the series and what's happening there.